Hello and welcome to lecture number 4. Because it's already dark outside, I can't with good conscience do my usual ritual of making a coffee, but instead I'm having a tea. So if you have whatever beverage suits your time zone right now, we are ready to get started. So the first thing I want to do is, if we switch to my main screen here, is to look at the resources page, because I have mentioned it a bunch of times, but I haven't really gone through it. And I want to really highlight some of those. The first one being R for Data Science, and it's a really great book. A lot of the course is actually based on R for Data Science. I even included some exercises from R for Data Science last week, which you have probably noticed. It's a great book to just work through. If you do the exercises while you're reading it, it's great, but you can also just read it as well. It's written by Hadley Wickham and Garrett Krollmund. And Hadley Wickham, who's now, I think, chief data scientist at RStudio, he's the one who started this whole tidyverse with inventing the dplyr package. So it's a great resource by true masters of their craft, which I really recommend. And the reason I'm going through these resources now is because lecture 4 sort of marks the middle point where we are finishing up most of the basic R knowledge that you need to know in order to free up our minds for the statistics in the coming lectures. So then we can focus more on the actual statistics and sometimes a bit mathematics as well. And don't have to worry too much about R. We can then just use R as a tool, as an extension of our brains, essentially. There's also a link here to the RStudio cheat sheets, which is a collection of all the individual cheat sheets that are linked to by their packages. So for example, this here, the ggplot cheat sheet. As you've seen, I have also linked the ggplot package with these little Hextag stickers you can click in the course script. But this just gives you straight the cheat sheet. All right, and these are really, really good. Just to look something up. Very, very handy. For our Markdown, there's also a very handy cheat sheet. And then there's the Advanced R book, which is also by Hadley Wickham, which I also really recommend. You don't really need it, but it's nice to know how things work, especially when things don't work as expected, of course. So if you want to go further, you can check out Advanced R as well. But I do recommend to go through this course and data science, R for Data Science first. There's also a craft cookbook, which is quite nice, which has a bunch of just little recipes for making crafts with ggplot. And then about the statistics part, we will get into when we get to the statistics. But I want to make some honorable mentions. For example, David Robinson and Julia Silge both have excellent YouTube channels and websites. And what they do, for example, is they work through a data set like we are doing, and they explain what they're doing. And it's amazing the way they think about the data, and they also explain it really, really well. So Julia Silge does a lot about modeling, which we'll get into later when we've done more statistics. And David Robinson also does some modeling, but more he focuses more on general data exploration. And yeah, there's a bunch more that you should really check out. All right, that being said, let's jump back into RStudio. I'm here now in this project for the course, and we talked about the resources. We talked about the goal for today, to bring everything together. This is also the reason why this lecture might be a bit more challenging than the others, because while everything now comes together, you basically need to know all the stuff from the previous lectures in order for things to make sense. But you can always go back, check out the script, check out the previous lectures on YouTube on this website. And what I want to open up today with is the concept of iteration. Before we do that, let's do our usual setup. I want to load the tidyverse. So I type library tidyverse. And I execute this code, and now I have the tidyverse functions loaded. So the example is, what if we want to read in multiple files and combine them into one tibble? And these multiple files I'm talking about, I have those in the data folder for today. So if I look into this data folder, 04 is for today. It's actually the Gapminder dataset that we worked with before. But it's split across the continent. So Africa only contains the data for Africa. And America, and then we have Americas, Asia, Europe, and Oceania. So how are we going to do about this? We know how to read in one file. Well, we can say read CSV, and then we type data, 04, and then let's say Africa. And this works. It's nice to confirm that it works on individual files. But we want to read them all in. So there's one way would be to go, okay, we need to get all the file paths, right? And a nice package for this is the FS package, which stands for file system, which comes with the tidyverse as well. So these functions or versions of these functions also exist outside of this package, but sometimes it's nice to have everything in one package, and then you know where to find stuff. So FS, and then there's dir ls, which stands for dir directory, and then list the contents of directory. And what we want to list, well, we need to give it a file path, and we want this. And we can, let me just keep this here, so I don't delete the data for the lecture script. Right? I should write down what we did here. So dir ls gives us the file paths, and we can open up the help page for this on the side just in case. Now, if we take the first element of this using vector subsetting, we get, like, using 1, we get the first element. Using 2, we get the second element. And now we could imagine to say we want to read CSV, and then say we only want to read in the second one, which would be the Americas. And this works. We are putting the second element of this path in here. And now there's multiple ways of going about this. And I want to show you the approach that I don't usually use first, because other programming languages use it a lot. And well, in R, you don't have to use this a lot, but it's there. Right, so I basically never use this one, but I want to show it anyways, because otherwise people will ask about, oh, what about for loops? And this is what we will be talking about. It's called a for loop. So what we can say is for, and then in parentheses, and then we are creating a variable here now. Say, let's make a little example first. Say for x in, say, the numbers from 1 to 5. And now we need these curly braces, and usually a new line. You don't need to, but new lines make it more readable. And then we can do something with x. Say we want to just display x as printed. And this will print the numbers from 1 to 5. Now in this case it's not very useful, because we're not doing anything with x. But what if instead of numbers from 1 to 5, this was our past? So let's take this here and assign it to a variable. So now we have called it pass, and we can use passes here. So we want to use these passes in here. And now every iteration, x will be this pass. And we can do something else with x instead of just printing it out. So we can say read CSV. And this will read in all the things, but it doesn't do anything with those because it just jumps straight to the next iteration. What we want to do in this case is save the result of this to a variable. However, if I just do this, result will only contain the result of the last iteration, so only Oceania. Because every time we run through this loop, we override this result variable. We can circumvent this by making result a list first. So let's say result is a list and doesn't have anything on there. And then it gets really annoying. We have to say we want the result at a certain position. So instead of iterating over over the pass, we need to iterate over the numbers from 1 to something that are as long as the pass. So 1 to length of the pass. And now instead of saying x here, and usually we call this I, we say we want the pass at position I. So the i's pass is saved in the results list at position I. And now results, if we go over all these warnings, let's look at our pass again. Right, what I did here is I used a single round bracket. I need 2 here, because otherwise I can't access a single list element. Okay, so now result is actually a list with all our different data frames or tables. And what we can do is say bind rows, and we want to bind this list into one table. And now we are back to the normal gapminder dataset. There's one extra step we need to do here. We don't have to, but R is not very good at making lists longer every iteration because it doesn't know how long it needs to be beforehand. So it doesn't really reserve enough space for it sometimes, so it needs to move things around, so it can get slower. We don't want that. What we want to do is, before we do anything, before we add anything into the result list, we need to give it a name first, a length first. We can do this using the vector function. The mode is going to be list, and the length is the length of our pass. And now it does the same thing, except in some cases it will run faster. Now, you might already see why I don't usually use this, right? It's a bit cumbersome. We are writing a lot of code that doesn't really do anything. It takes a while to read this code and know what it's doing. I call this the imperative approach because in imperative programming, we are telling the computer exactly what we want the computer to do. So it's very imperative. As opposed to the functional programming approach. In functional programming, we usually don't tell the computer the exact steps it needs to perform. We tell the computer what things are and what we want them to be. And then usually the computer figures out, or R figures out, what it needs to do in order to get there. And there's a great quote by Jenny Bryan, who's also working at RStudio, and she's a professor at, I don't remember. But the quote goes, of course someone has to write for loops, it doesn't have to be you. So along the spirit of that, let's not write any for loops anymore and do the same thing, but without a for loop. All right, one thing I want to remember is we still have this one, so let's copy it down here. Even though technically we still have it, we don't need to recreate it again. let's just copy it down here so we can compare those two approaches with all the code they need. So we have our parse, and notice how in all this boilerplate code that we're looping over stuff, we are creating a results vector to hold our results. We are creating an index from 1 to the length of our parse. The only thing we're actually doing, the only important thing is this read CSV part. This is the function we are applying to every element of the parse vector, and we're saving the result in the results variable. And there's a way more straightforward approach to this. So in mathematics, this is called a map. So we have a set of an input set and we have an output set. And in this case, our input set is just these parse, and our output is all the data that we are reading out with read CSV. So what we want actually is a map from our input set to our output set. And we have a way of getting from one point in our input set, one parse, to one point in our output set. So read CSV of, say, one element of the parse. Oh, it's plural. I made it plural. It takes our point in our input space, right, one parse, and it returns our output dataset. And what we want to do is just map this function over all our input, over the complete input vector. And this is exactly how we write it in R. So we want a map. And the first one is a list of atomic vector. This is our input. And the second argument is a function. And the function is read CSV. Notice I'm not adding these parentheses here. I just want the function name. So we're just passing the function without calling it. The calling will be done by map. And this happens now. So map returns a list. And it returns a list. And every element of the list is the result of applying this function to this element. Now we have this list. And we can call bind rows on the result. Now this operation is so common to just make something a tibble that there is a special variant of map. So let's take this here. Instead of saying map, we type an underscore, and the autocompletion tells us all the variants of map we have. So usually map always returns a list. Well, it's reasonable because lists can contain anything, even other lists and stuff. So it will always fit into a list. But if we know what we want, and in this case we want a data frame, df for data frame, we can say we want this result to be a data frame. And we get the data frame straight away. There's another step we can do, and this is, right now we have lost the information about where it came from. So let's add this back in. There's the .id argument to the mapdf function. And this wants a name for the column to create. Let's call it continent. And this column will come from the names of our input vector. So you may have missed it, but if we look in the help page of DLS, which we used, it's the same as the normal ls command, but we have the names of the names of this vector. So the vector already has names, and the names are just their values. And these names will then be used to create this column. So now we have a bunch of stuff around here. And this is why I want to introduce the string R package at this point. So we have worked with it a bit, but I want to really highlight it here. It's very, very handy whenever you have to work with text. And whenever I have to work with text, I also often have to look at this cheat sheet. So in this case, what I want to use this for is inside of mutate. I want to change the continent to be string remove. And let's close this here. But you should check this out if you ever have to work with text. So from the continent column, I want to remove a pattern. So we only want this Africa.csv. Actually, instead of saying remove, let's do extract. Let's see how this goes. I'm not going to go into the details of how we're doing this, but I want any number of anything that is followed by .csv and preceded by a slash. And this gives us a bit too much because it matches everything until the first slash as well. We only want any word characters. So this will look very, very cryptic, but please do have a look at the cheat sheet, which explains how these things work. So this one here is a look behind, and this is a look ahead. And this is the actual part we are matching. So we want any word characters, and we want as much as you can find, which is the plus symbol. Word characters are anything that is not punctuation, like slash point or something. But it should be preceded by this slash symbol. And afterwards, there should be this .csv. So we're only taking the middle bit. And now we are back to the normal Gapminder dataset, actually. So let's call it Gapminder at this point. Now this was an example of explicitly using a map. However, the readr package is already what we call vectorized. So the function readCSV, and I'm not sure this is even documented in here. No, it's not set in the file argument. But what I'm telling you now is this trick that readCSV already takes a vector of file paths and will combine those automatically. So we can take all our paths and read those in at the same time. We are still losing the continent column, but there's an ID thing. And there it's document that takes multiple things. And now we have the same thing. We could do this part again, but actually, because we will be using the country colors later on as well, let me go ahead up top and actually load in the Gapminder package, which has the dataset and all the surrounding stuff. So I want to give you a little roadmap on how you can go ahead and, oh, I just did that up top. Why am I doing this down here? And on how you can go about solving any programming problem. So you encounter a problem. The first thing you should ask is there a function that already solves my problem? For example, reading in a file, there's read CSV. So yep, it already solves my problem. And now I encounter multiple files I want to read in. So the first question I ask, is my function already vectorized, right? Can it already deal with multiple things? And then I don't need to do any extra work, I'm fine. If not, and then I encounter a different problem, I try to solve it for one instance of the problem first, right? Reading in one file, for example. Or, I don't know, solving one mathematical equation, for example. So is there a function that solves my problem just for one example? And then I can go ahead and just take all my examples and map the function over them. And then I have solved them for all. And then you might also have to decide on the type of output you want. Map always gives you a list, but if you want, say, double, which is text, which is numbers data, double precision numbers, or CHR for character, for text, this will then give you a regular vector, no longer a list. Or int for whole numbers, integers, logical for Boolean values, yes or no, true or false. And then there's a bunch of variants of those, which I'm not getting into today. Map2, for example, is if you want to simultaneously map over two different inputs. Say you have a list of files and some special arguments of what to do with those files, maybe, and then one function that takes a file and the special argument. You can map over those in parallel. I want to highlight writing functions a bit more, because it can be very, very helpful. Let's actually take what we did up here, this part, and let's just copy it down here. And we have the paths. Let's actually get those as well. Let's say this is some way we are reading in our data every time we're doing a certain experiment. And this machine just outputs this data in this weird format, which is spread across multiple files. We need to do some cleaning up first. So what could happen then is you're doing this experiment, you analyze your data, you're doing the experiment again, so you go back to your old code because you're clever, so you copy and paste your code, right? And then you're ready to use it. And this works perfectly fine. There's nothing wrong with this, but there is an easier way to do this. Instead of copy and pasting, we can create a function that does that and then call this function every time. So let's take this whole idea of, okay, we want the path to a directory. So the first step would be to identify what's changing every time by using our code. And in this case, maybe the different experiment would be in different folders every time. Right, so maybe we have a folder for every day we did this experiment. So we would write a function that takes, let's say the function takes a day, and then it creates the parse and reads in our data. So let's create a function called read experiment data. And it takes, let's make it a day. Because let's say we are doing this experiment every day and we're storing them in our data folder and we're always saying this is day 1, day 2 and something. So let's put this in here. So first we need to create these paths. And I'm using this as an option to showcase the function paste. So let's surround this again. Whoops. So the function paste or paste 0, let's actually do this down here so you can see what's happening. It combines text. And say we put in the day here. Right now day has no value. Let's say the day is 1. This is how it would look like. So we can use this, for example, to create our file path. I'm using the paste 0 here because normal paste adds a space in between everywhere. And paste 0 doesn't do that. All right, so the function takes the day we did the experiment. It creates the file path to our experimental data. We are then reading in our data with whatever processing we are doing. And actually in this case, it's a bit annoying because I called these folders day 0, 1 and something. So can string_r do this? Yes, it can. Okay. So we need to pad this to a number of 2 with zeros. So we can test this function now. And we want day 4. Oh, it's just 4. And right now this is not working because day I changed the arguments of width and pad. So the width would be 2, but we want a pad with zeros. And now we can read in the data from day 2. It doesn't work for the other days because, well, there's different data in here. But in the theoretical thought experiment of having the same data for different folders, this would work. Now, this still doesn't help you if you now have to copy and paste this function, right? You need to get your function into your analysis script every time you're running an analysis. So one way to go about this is to create an R script. Let's do this now. And in this R script, we define this function. and we save it. Let's create a folder called R my functions.r. And what we can now do, instead of doing this here, we can call the function source. We give it a file path, and all source does is it runs this whole script. And because all the script does is define a function, we can then use this function just like here. So you have a file, and you can then source this file everywhere you like. You can use this, for example, as well to create a custom ggplot theme that you're using everywhere. Now you could go one step further and actually create an R package. It is fairly straightforward. I'm not going to do this now, but if you go into a new project, say new directory, and you can check, instead of project, you can check R package here. And then you can install this R package like you install other R packages, and you load it with library and then your package name. This can be a nice way if you have a lot of functions that you're using like multiple times. All right. Oh, we basically talked about this. Yep, that's good. Now I want to come back to the point of implicit iteration, that sometimes we don't do explicitly map over something. We can do it implicitly because R knows that we want to do something to multiple things. And one of those instances where this pops up is again with our trusty dplyr package. I want to create a little example for this. Let's say we have this gapminder package again, and let's first only look at one country. Let's actually use first one here, Algeria. And now we have only Algeria. And let's plot this. So what we notice here is it's quite a straight line here. Over the years, the life expectancy goes up. And we might ask the question, how straight is that line? How well does this fit a linear model? In ggplot, we can already add a linear model, using geom smooth. And as the method, we choose lm for linear model. This even gives us a little confidence interval around it. But what it doesn't give us is any numbers of how well does the line fit to our data. And usually I would probably put it the other way around. So we're not covering our points with the line. So in order to do this, we need to create the model as ourselves. And we are not going to go into the details of how linear models work. We will dive more into those when we talk about correlation as well, because there's some related and there are some relations, but some differences. So let's just look at this as fitting a line as best as we can. And then we later want to get some notion of how well this fits. So in order to fit a line ourselves, we need the lm function, which stands for linear model. And the first one is going to be a formula. And whenever it says formula, we need this little tilde symbol, like this squiggly line. And we want how linear is the relationship between something depending on something else. So we want the life expectancy and then tilde depending on the current year. Now this will not work because R does not know where to look for the life expectancy. But we can tell R that the data comes from Algeria. And now linear model will look for life expectancy as a column of the dataset Algeria. If I can type correctly. Now we get this linear model. Let's save it to a variable, and instead of just displaying it here, let's call the summary function. There's a big difference between summarize from dplyr and just summary. We will mess this up a bunch, I guess. So we need to run this first, of course. All right. There is lots of information here, which we're not going to cover today. But one important bit is this multiple R squared and adjusted R squared. This is a measure between 0 and 1, and it tells us how well our line, where's the line? Oh, there's the line. How well our line fits the data. So 1 would be a perfect fit, and 0 would be the data is all over the place, and a line is it doesn't fit it at all. So it's a very, very good fit. It's quite linear. There is a nicer way to display this data from the model using the Broom package. And Broom has a function called tidy, which takes the model and displays it as a tibble. And tidy tells us, for example, nicely the intercept and the year. So every year, the life expectancy increases by 0.5. And this is the intercept. This is would mean that basically at year 0, we would have a negative life expectancy, which of course makes no sense. This is not how time and life expectancies work. But we are of course only fitting a portion of the data, and we don't have any earlier data. So sometimes you can't really extrapolate this as much as you like. But for this part, it fits very well. And of course, we wouldn't want to extrapolate this to the year 4000, for example, unless, of course, people get 140 years old by then. Maybe they do. We'll see. Another nice, let's put this here, function is the glance. To get a quick glance, just like the summary. It's a bit like summary. The glance function, but a bit more organized as a tibble. So we get the R squared as well. And from this, of course, we can get the R squared. If we only cared about one number. So we want this number for all the countries. So one way we could think about this now is we could write a function that takes just one country. It filters our data. It then fits our model to the filtered data, and it spits out this R squared. And this is certainly doable, certainly feasible, but there's an even easier way to do this. And this is just with the dplyr package. So let's take our gapminder dataset. And what we want to do is group by country. Let's also group by continent. It doesn't add anything because country is already within each continent. There's no country that is in multiple continents, but it means we're not losing the continent column in whatever we are doing further. And then we can summarize. So we create a model in here that is a linear model of life expectancy depending on the year. We don't need to give it the data argument because it's all inside of summarize. So it will already look in the Gapminder data set. And it will do this inside of our groups. Now this part will not work straight away. And the reason is, well, model must be a vector, not a LM object. Now that's a confusing error. And the reason is, well, the LM function returns this model object, but dplyr only wants us to have regular vectors. Because every column in here we see, every column is just a vector, right? Life expectancy is a bunch of numbers, population is a bunch of numbers. But remember that columns of our data frame can also be lists, a list column, and lists can contain anything, even models. So if we make this explicitly a list, this will make the list column, and list columns are allowed to contain anything, and then it's suddenly fine. Right now we have a column with a bunch of models, and we can work with this column. I want this R squared. How are we getting this? We want to take a function that takes a model, and let's do this here. Get R squared is a function that takes a model and it does just this part here. So we define this function here. And now we can map over the model column the get R squared function. And what this does, it adds another column to our data set. But you notice it's a list column as well. And this is because the map function by default always returns a list. So we have this sort of pointless list, right? It's a list where every element is a length 1 vector with just the number in there. But we can't see the number in here because that's the way lists are displayed here. So we want to tell the per package, which supplies us the map function, that this can be just map double. So just get the number, give us a normal vector instead of a list. And now we got our R squared values. Let's save this to a variable. And now, what we can do is take our original Gapminder dataset and join it with the models. Actually, we don't need the model column anymore. We only care about the R squared value. It's otherwise going to be like a really big data frame because there's a bunch of models in there. So let's select from all models, everything but the model column. And now we have the R squared value. Now it's of course duplicated here because we have one R squared value per country. But in this format, we have all the years for each country. So we can use this now. Let's actually override the Gapminder variable. And let's make a little plot We are plotting life expectancy over a year. Color is gonna be the country. Before I forget, let's do this now. We remove the legend. And then we're adding some points. No, let's actually add some lines. And scale the color manually with the values being the country colors from the Gapminer package because I cheated. And now let's make this a bit more readable by using facet wrap. By continent with 3 scales. And let's also, I think I set a global theme for this whole thing, so it will look differently when knit. But let's add one here. And now, because we have this information here, we can use the R squared to make, say, the brightness or the transparency of each line proportional to the R squared. So we say alpha. What's it called? R squared. Oh, and actually, we want to do it the other way around. We want the more interesting lines to be less transparent. So a high R squared means it's very linear. It's a sort of a boring trend. There's nothing interesting happening in that sense. So we want the lower values where stuff happened to have a higher alpha value. So we do like 1 divided by, for example. And then the lower the R squared, the higher our alpha value is. And we could play around with this a bit more. But there's another way I think we could visualize this data, which is to say, we take our plotting code. We don't do this alpha thing. And let's first add just black lines with some transparency. And we need to group by country as well. And then we highlight those lines which have these large dips by adding them again. Where without this modification, but where the data is our Gapminer set filtered to be, or we can use one of those slice functions. No, actually we can't. Damn it. We want to filter for the R squared to be, say, less or equal than 0.4. All right, those are these lines here in Africa. But for context, we can leave the others in here, of course. And then I wanted to show you one last trick for labeling things. And this is the ggRepel package. You can install it using install packages ggRepel. And this gives us another geom called geom text and label repel. So we take this for these data sets as well. We also filter for year to be the maximum year. And ggRepel needs an aesthetic called label. As the label, we just want the country. And this error is because I just set AS country. The first argument to AS is X. We don't want to change X, we want the label to be the country. Now that was confusing. Now we get these labels in here. In order to see this better, let's actually filter this now. We need double equal here. And now we can add another argument to geomRepel. We can tell it to oh, there's a bunch of options here. Oh boy. I believe there should be the vjust argument as well. Oh, hjust, I mean, for horizontal adjustment. This is how our text is going to be aligned. And let's make some room for our labels by expanding the x-axis. By, let's say, 10%. Yeah. Maybe 20%. Oh, we only need to do this on one side. So let's create a vector 0 on the left side, 0.2 on the right side. And we can nudge them around a bit. Maybe this helps. Ah, yeah, we're getting somewhere. Okay. So what geomRepel does is it allows the labels to repel each other, and they're connected to the lines via these other lines. We can also tell it to only dodge in one direction, which would be the X direction, Y direction here, for example. Yes, okay, now we're getting there. Okay. And at this point, we probably want to make the lines a bit thicker. That's a bit too much. All right, this should be enough visualization for today. There's one last note I want to add, and that is in the chunk options. There's a bunch of options. One of those is the fig.cap, which is the figure caption, which is very handy for scientific writing, for example. And what I have just done is I hit Ctrl+Shift+K to knit everything. And we will see how this will look like on the final website. Let's go down here. And we have our figure caption. And because we are in this book down project, it also added figure labels. Now there's one extra trick I wanted to show you. And this has to do with figure captions as well, because when you have longer figure captions, it can get very annoying. Say you have some more options as well, like the figure width, for example, and the figure height. Yeah, this looks good. So you have all these options, and at some point, they all need to be on one line, but it wraps around, so it gets very unwieldy. So in the new version of the R Markdown package, there is another way of adding these options. So let's show you here. You add a comment and this pipe symbol, which is another pipe, sorry, this bar symbol. So a comment bar, and behind there you can say fig.cap. And then instead of an equal sign, we need a colon. And then you can type the figure caption. So let's do this. And you can use like both ways of writing it. They will be merged in the end. So this is the same way we are writing figure captions or giving arguments to chunks than in the header of our Markdown document. Remember the metadata I showed you? It's called a YAML header. When we introduced our Markdown in lecture 1, actually. So it's the same way of writing things. And in this case, it didn't work because I haven't updated the Markdown package yet. Okay. And let's just check. It might actually even be backwards compatible, so you can still use the dot command. Let's just try this out, let it run in the background. But if there's nothing really surprising there, that's all I have for lecture 4 today. I'll upload the exercise as soon as they are ready. And let's have a look at this final output. All right, it works as well. So you can use figure.cap or figure -cap in these magic comments as well at the start of a code chunk. All right, I'll see you in the seminar then.